This is the second video looking at Level 3 experiments or Achievement Standard 91583 for Level 3 and Scholarship Statistics students. So now we've talked about experiment design and setup, we're going to look at what to do with the data. So in most situations you're going to be given this as a box and whisker plot, or you need to create that box and whisker plot if you're running your own project. And then you'll compare the outcomes of what happened to the thing that you were measuring under the different conditions you were testing for. It's very much like formal inferences again, so looking at comparing those differences between two groups. And most often you're going to compare the median or the mean, and you'll choose which is best for whichever situation it is you're dealing with. If you expect there to be skew, then you should go for a median measurement to compare. And in fact, in most cases, the median is the better of the measurements to make those legitimate comparisons. Then you make a call based on the difference compared to the overall visible spread, or by using a confidence interval from bootstrapping. That's most likely what you will do is the bootstrapping method, like you do in formal inferences. Then you can investigate the results of re-randomization of your data to test to see if it was just something that happened by fluke, or whether the difference that you've observed is statistically significant. So let's talk a little bit more about what that re-randomization thing is. So randomization we talked about before, where you randomly allocate your participants into two different groups. Re-randomization is once you've done the experiment, you then take all of your pieces of data and you mix them all up and you randomly split them into two different groups to see whether you could have just accidentally come up with the difference that you've seen in your experiment just by pure chance. So what you do is you're checking for whether the observed difference that you've seen in your experiment could have just happened by chance, if it could have just been a fluke. And we do that by putting all of the data back into a pot. Put all of your bits of information, regardless of whether they were in control or treatment group or before and after, whatever it is, put it all into one. Then randomly select the data and reassign it to each group. So whether it actually was originally control or treatment then becomes totally meaningless. You just put it into a group which you will label as control and treatment. Then you compare the two groups in the same way that you did originally on the experiment. So for example, looking for a difference of median or mean. You repeat that process 1,000 times to see the likelihood of the difference that you originally observed in the experiment to whether that could have happened just by chance, which is what we're doing right now. We're seeing, could we have got this by chance by just randomly allocating these people to two groups or participants to two groups? Could we have ended up observing the difference that we saw just by fluke? So the differences will be centered around 0 because of the random assignment. They should have a similar median or mean, these two different groups that we're doing, if things were happening purely by chance. So if the experimental difference that we saw to begin with has a very small chance of happening on that re-randomization, then we can make the call that whatever happened in our experiment was statistically significant, because the chance of it having happened purely by chance alone is not very big. And vice versa, if the chance of getting that observed difference is reasonable, and we usually go for 5 to 10% or more, if we get a chance out of that, then it means that actually this could have just happened by chance. The likelihood of it happening on its own is too big for us to say that our experiment is statistically significant. So this is the call that we make, is that if that re-randomization shows the chance of our differences that we observed was less than 5%, then there is evidence that these results were not produced purely by chance acting alone, because the likelihood of having seen that difference is so small. It's likely that the intervention caused the difference that we observed. And the other way around, if it's more than 5%, it's possible that the difference we observed was just due to chance alone, and we can't make the call that the intervention that was part of our experiment has actually caused the difference that we observe. Now, 5% is a rule of thumb. We don't go exactly for 5, and in some books you might even see it as 10. So it is just a general judgment call around where we say that it's too big or too small. This is easier to explain with an example. So we will take a look at this experiment that was done with some rats completing a maze. And in the first maze, they put peanut butter as the thing that the rat was trying to find. And in the second maze, they put chocolate. And they're trying to see which of those makes the rat complete the maze faster. So which one is going to be a better thing to put down as your thing to attract rats and maybe get them into a trap or something like that. So obviously the lower the time, the better, because it means that they are completing the maze faster. So the first thing to note is what our box plot shows us at the top. So we've got a median for the peanut butter target being 40 seconds, and the median for the chocolate target was 46 seconds to complete that maze. Then down here we have a bootstrap distribution. So we put that back in the same way as formal inference. Just go back and revise that if you're not sure what's happening here. It's done 1,000 times to see what we can expect the difference of those medians to be. So we can now read off that we expect the difference between the medians for the rats going for peanut butter to be between 1 second and 16 seconds faster than the median time to complete the maze when the rats are going for chocolate. So we've got that confidence interval before, but we actually want to know if it's statistically significant enough of a difference to be able to say that putting chocolate in there instead of peanut butter is what made the difference to making them complete the maze faster. So we do this re-randomization distribution, which is the difference between the medians of those two groups. So what's happened here is we've put all of the data back in, all of the maze completion times back into one pot. You randomly pick out those and you assign them to having the label of chocolate and peanut butter, and then you work out the difference between those two, the medians of those two groups, and you plot it down here on the dot plot below. So you do that 1,000 times and you build up these dots into a distribution. So that re-randomization has happened 1,000 times, and now we have a calculation over here that works out what was the chance when it just happened randomly in this dot plot distribution, how many of those random groups came up with the difference that we observed here of a difference of 6 seconds. How many of these groups down here had that difference of 6? So that's what we've got right here. We're looking at the edge of our distribution. We can see it's right at the top end. So we've got 2 of those random groups that came out with a difference of 6 seconds or more. So 2 out of 1,000 is really, really small. So the chance of that happening, that difference that we saw of 6 seconds of happening purely by chance alone, is really, really small. It's 0.002 or 0.2%. So that's right on the extreme of things, which means that it's highly unlikely this happened by chance alone. And we can make the call that giving the rats the target of peanut butter improved their maze time score. And this is how you'd write it up. I'll just give you a minute, pause, read it, click play. Now, once you've made that call, you need to consider the limitations of your experiment. So the conclusion reached is only applicable to the group that was studied. It can't be used to make an inference about the whole population unless that group was also randomly selected to be representative of the population. So there'd be some things to consider there to say whether you could apply this to wider than the group that you did it on. But what you could discuss is if that group is representative of the population, what that would mean and what other judgment calls you could make if the group had the same kind of characteristics of the population and that kind of thing. You also need to consider what other things might have gone wrong within the experiment, what sources of variation there were. So on the rats one, for example, did we make sure it was exactly the same maze and that the rats hadn't seen that maze before? Because if you were doing them in the maze first and then you got the same rats to do the same maze but with a different target, they should naturally get better anyway because they already know the maze. But it could be something a little bit more complex than that, thinking about other factors that could have affected your experiment, discuss whether it would have made, what impact it would have had on your results, what kind of difference it could have made, and whether it would change the type of call that you've made about in your conclusion about the results of that experiment.